Okay, our very little brief stint into electrochemistry to redox reaction balancing. If you're taking Chem 2, you will be balancing redox reactions. So we're talking about it a little bit now, partly because of that. So we hopefully remember from chapter 5, the end of chapter 5, a little bit about redox reactions. We've got our mnemonic device oil rig, and we've also got Leo the lion goes grr. To remember that oxidation is losing electrons, or losing electrons is oxidation. Reduction is gaining electrons, or gaining electrons is reduction. Either way you want to remember it, or both ways, it doesn't matter really to me. We also have our definitions of oxidation being an increase in oxidation state. Remember that oxidation state is this little fun made-up game that we do to kind of keep track of who's got the electrons. And it's often a similar number to the charge or the same number as a charge, but it's not the same thing as electrical charge. Again, it's a made-up game to keep track of electrons. So one of the things that makes redox reactions complicated is that mass has to be balanced. We're familiar with balancing mass. We've balanced chemical reactions before. That's not new to us. But charge also has to be balanced. So when we're doing redox reactions, we often have a different charge on the left side of the reaction versus on the right side because there's electrons being transferred. The electron transfer is always implied, it's implicit. We're not explicitly writing out in any of our reactions where the electrons are on one side or the other, and it all needs to balance out. So there's a whole lot of behind the scenes sort of stuff that we have to do to separate these out. And so it's this charge component that really makes redox reactions more difficult than regular other reactions that we've done before that aren't redox. So the way that we're going to do this is we're going to break our equation into two half reactions. We'll balance them individually, and then at the end we'll balance them back together or add them back together. Okay, so if we want to do this, the easiest way to do it is in acidic solution. Basic solution is not much more difficult. There's just one extra step, and there's a fun trick for how to do that. So the first thing that we want to do is assign oxidation state. So we have to know our oxidation state rules. We have to know what numbers we assign to what things. And then we have to identify the substances being oxidized and reduced. So assign numbers, identify, identify, reduction, and oxidation. This is so that we can split our reduction and our oxidation separately. We're going to treat them as separate processes. We're going to separate that overall reaction into the two half reactions. So we're going to separate our redox from oxidation. So we're going to do balancing these two things separately. And then we're going to balance them with respect to mass. So balancing that we've normally done for the elements, balancing for the elements. We're going to balance everything other than H and O. So balance the elements, things that aren't hydrogen and oxygen. And then, critical to this, we are working in acidic solution, an aqueous acidic solution. In aqueous acidic solution, since it's aqueous, we've got a lot of water. Since it's acidic, we've got an excess of H+. We'll usually just talk about it as H+ rather than thinking of it as hydronium ions, even though that's basically what it is, because it's just easier. So we can balance everything other than hydrogen and oxygen, things that aren't just naturally in an acidic aqueous solution. And then we can balance the oxygens by adding H2O. Because we're in aqueous solution, and so there's an unbelievable amount of water already around. It's all over the place, so we can just invoke, hey, there's some water around, it probably participates, and that would balance out the oxygens. We can then balance the hydrogens by adding H+, and this is because we are in acidic solution. And in acidic solution, H plus is around. Acidic is defined as having an excess of H plus relative to hydroxide. And then we can balance things with respect to charge. Balance charge with electrons. So we can add electrons either to the reactant side or the product side to bring down the charge on that side. Since electrons have a negative charge, if we're adding electrons to one side, we're reducing the charge on that side. I feel like this part can often be confusing for people. It's arguably more critical than before that we keep track of our work and we're diligent about writing out all of our numbers, because there's a lot of places that we can screw things up. Redox reactions are one of the places where I make the most mistakes. Okay, so we balance our charge with electrons, again, bringing our charge down. And then we can make the number of electrons in our half reactions equal. So we want our number of electrons to be balanced between equations or between half reactions. So if our oxidation half reaction has 5 electrons, then our other reaction, our reduction half reaction, has to have 5 electrons, and they should be on opposite sides. What this does is then it allows us in the next step, in step 6, we can add the two half reactions together. Since we would have had 5 electrons on the side of one of them and 5 on the other side, we can cancel them out. Anything that's on the left side we can get rid of that's also on the right side. So that's how we get rid of the electrons. That's where they disappear. That's the step where they go away. And then at the very end, for redox reactions, I really recommend that you actually go back and recheck everything. Verify that the reaction is balanced with respect to mass and with respect to charge. Again, because we've got so many moving parts, for redox reactions, I recommend that everyone go back and check their work. For balancing normal reactions where we're not doing redox stuff, it's kind of optional because usually you keep track of everything, but with redox reactions, sometimes we make a mistake multiplying, dividing, canceling things out. So we want to make sure that we've done our due diligence. All right, so we've got all of our rules, kind of the shorthand over on the right side. And we're looking at here like the most basic redox reaction. Okay, so our first step, we need to assign our oxidation states. For neutral, natural occurring forms of elements, they get a charge of 0. So our aluminum and our copper get oxidation state numbers of 0. For things that are ions, like copper and aluminum, they get the same oxidation number as their charge. So +2, +3. So that's our step 1. For step 2, we want to separate into separate redox reactions. So our reduction gets pulled aside, our oxidation gets pulled aside. You don't necessarily have to label them, so you don't necessarily have to have these definitions of redox in your head. You should have them, but you can also just separate them out. So we've got aluminum as a solid going to aluminum ion. This would be our oxidation half reaction. Our other reaction is our copper 2+, our cupric ion, reverting to its natural copper form. This would be our reduction half reaction. For step 3, we balance the half reactions with respect to mass. So balancing other elements, things that aren't hydrogen and oxygen, they're already balanced. Balancing oxygen by adding H2O, we don't have any oxygen. Balancing hydrogen by adding H+, we don't have any hydrogen. So it's already balanced, and so we're just going to do the charge part. So now we want to balance our half reactions with respect to charge. So let's take a look at what are our charges. For our aluminum half reaction, we've got neutral aluminum on the left side, which has a charge of 0. On the right side, we've got a 3+ charge from our aluminum ion. For our copper half reaction, we've got +2, or 2+ on the left side, and we've got 0 on the right side. To balance our charges, we can add electrons. When we add electrons, electrons are negatively charged, so we're going to add them to the side that has the higher charge. So for our aluminum half reaction, we need 3 electrons on the right side. 3 electrons will cancel out our 3+ charge, and now we're back to neutral. For our copper half reaction, we've got the positive excess on the left side, so we're going to add our electrons to that side. If we add 2 electrons in, that cancels out our 2+ charge. And now we're back to neutral. So that's our step 4. And then for step 5, we want to make the number of electrons equal. So we've got 3 electrons in our aluminum reaction. We've got 2 electrons in our reduction half reaction. What number can we get both of those to? 6. Yeah, we can get them both to 6. So 3 times 2, 2 times 3. So we're going to multiply these reactions. All the coefficients get changed in order to get our electrons to 6. So 3 and 2 both factor into 6. 6 is the least common multiple. So we do that multiplication, and I'm going to stack them. So we've got 2 aluminum plus 2 aluminum, going to 2 aluminum ion plus 6 electrons. And then we've got, for our copper reaction, 6 electrons plus 3 times the copper ion going to 3 times copper metal. And then we can combine them. So combining them, we'll have 6 electrons. It doesn't really matter what order you write these things in, plus our 3 copper ions, plus our 2 aluminum metal. That's on the left side. On the product side, we've got 3 copper metal, plus 2 aluminum ions, plus 6 electrons. And since we've got 6 electrons on the left side and 6 electrons on the right side, we can cancel them out. And then the last thing to do would be to check and make sure that we've got everything still balanced up. So we've got 2 aluminum on the left side, 2 aluminum on the right side, 3 copper on the left side, 3 copper on the right side. We also have to look at charge. So we've got 3 copper ions that have a 2+ charge each. That's a total of 6+ charge. On the left side, we've got 2 aluminum ions that have a 3+ charge each. So we've got 6 positive charges on the right side. So it's balanced with respect to charge also. It doesn't have to be a 0 charge on the left and a 0 charge on the right. It just has to be the same charge on the left and the right to ensure that we're not magically poofing or appearing electrons or charge. Questions about that? Okay, let's step up the difficulty a little bit. Okay, again, we are doing the same steps. We're assigning oxidation states. We're balancing this in acidic solution. So let's go through and find our 0 charge items. We've got chromium. Chromium normally exists as Cr. and we've got hydrogen gas, which normally exists as H2. Those both get a 0. And then we've got hydrogen with a 1+ charge, and so it gets an oxidation state of +1. We've got chromium with a 2+ charge, and so that gets an oxidation state of +2. We can then separate these into their half reactions. So the hydrogen goes on one of these. The H2 will go on the right. The chromium is our other half reaction. So chromium going to chromium 2+. For our hydrogen, since it went from a 1+ to a 0, this would be our reduction half reaction. Our chromium would be our oxidation half reaction because it went from a 0 oxidation state to a +2. Now we can balance these with respect to mass. For chromium, it's already balanced. There's no other elements. We've got one chromium on each side. There's no oxygen, there's no hydrogen. For our reduction half reaction with hydrogen, we've got one hydrogen on the left, two hydrogens on the right. So if we add a coefficient of 2 in front of our H+, it's balanced with respect to mass. Not particularly complicated. This is just like one step up in difficulty from our previous problem. So we're balanced with respect to mass. We need to balance with respect to charge. So looking at charge, for our chromium, we've got Cr metal on the left side, no charge. On the right side, we've got our chromium ion, just one of them, so it's a 2+ charge. To balance these out, we can add in electrons. Electrons have negative charge. We're going to add them to the side with the positive charge to get that charge number down. So 2 positive charge means that we add 2 electrons. And that brings us down to neutral charge, even on both sides. I'm going to scooch my reduction half reaction over. For our reduction half reaction, on the right side we've got H2, that's neutral. On the left side, what is our charge? 2+. We've got 2 hydrogens with 1+ charge each. So we've got 2+. To get those charges to balance, we can add 2 electrons to the left side to even up our charge numbers. So now that we're balanced with respect to charge, we can make the number of electrons equal. Conveniently for us, they're already equal. So we can skip to just adding the half reactions together and canceling things out and simplifying and all that jazz. So we get 2 electrons plus 2 hydrogen ions plus chromium goes to hydrogen gas plus chromium 2 ion plus 2 electrons. Since we've got 2 electrons on the left, 2 electrons on the right, we can cancel those out. And then we can go through and check everything. We've got 1 chromium on the left, 1 chromium on the right, 2 hydrogens on the left, 2 hydrogens on the right. We've got 2 times 1 positive charge on the left for a 2+ charge. We've got a 2+ charge on the right, so we're all balanced with respect to mass and charge. Hopefully not feeling too bad. And now one where we do a little bit more. Okay, so we want to balance this redox reaction in acidic solution. First thing we want to do is assign our oxidation states. So our oxidation states are +2 for iron 2+, +3 for iron 3+. We also have manganese 2+ ion on the right side, so that'll get a +2. And we've got the permanganate ion. Permanganate ion needs to have an overall -1 oxidation number because it has a 1 negative charge. Our oxygen will get its preferred -2. It's also ionic, so we could assign it that way. But we get a -2 for our oxygens, so from the oxygens we're getting -8. We have to have an overall -1. So what charge does our manganese need to have to balance? Yeah, it has to be a +7. Yeah, question.
So on the oxidation states rule cards, it says priority, metals go before, I guess, the non-metals. In their compounds, metals have a positive oxidation state to their ion charge. So I guess I might use some oxide.
So for the permanganate, the MnO4 minus, we can also assign that values based on it being ionic. If we treat it like it's ionic, oxygen forms a 2- charge, so it gets a -2. Manganese would have to take up a +7 because it can have variable charge. So that'd be the other way that you can come about it. Either way, you should get to the same conclusion. Okay, so we've got them assigned oxidation states. We need to separate them. So we'll put our Fe2+ on the left side, going to Fe3+. Our oxidation number is going up, and so this is oxidation. And then our other one is permanganate, MnO4, going to manganese 2+. And this is a reduction because we went from +7 to +2 for our oxidation numbers. Now we can balance things with respect to mass. So looking at the elements, for iron, it's already balanced. Nice. For manganese, it's not balanced. Our manganese is balanced. Our Mn is balanced. We've got 1 and 1. Our oxygen is not balanced. We've got 4 and 0. So to get our oxygen count up, we're in aqueous solution. We've got lots of water around, so we can just say, hey, maybe there's 4 waters floating around. So if we add 4 H2Os to the right side, now we've got 4 waters, or 4 oxygens. Is it balanced? It's not balanced because we just added a bunch of hydrogens. And so now we need to balance our hydrogens. We've got 0 hydrogens on the left side, and we've got how many on the right side? We've got 8 hydrogens on the product side. So to get 8 more hydrogens on the left side, well, conveniently for us, we're in acidic solution. Acidic solution means we've got H+ floating around. So we can just say, well, we've got 8 H+s that helped out on the left side. So that gets our hydrogen count up to 8. So now we're all even with respect to mass. And now we do the special thing. We do the balancing with respect to charge. So we need to count up our total charge. For our oxidation half reaction, that's the one with iron, we've got 2+ and 3+. For our reduction half reaction, we've got 8 times 1+ and also 1-. So we've got 7+. And on the right side, we've got 2+. The way that we can balance out charge is with electrons. So we have to add in electrons. Electrons have negative charge. I'm going to do this in purple. So we can add 1 electron to our iron half reaction to the 3+ side. The 3+ and the 1- makes 2+. So now our charge is balanced out for our oxidation. For our reduction, we've got 7 plus and 2 plus. How many electrons do we have to add to get this 7 plus down to a 2 plus? 5. So we add 5 electrons to the left side. Our 7 plus is now a 2 plus. We're charge balanced. And now we have to get ready for merging these two together. So we get to do some multiplication. We need our number of electrons to be equal. In our manganese half reaction, our reduction half reaction, we've got 5 electrons. We've got 1 electron in our oxidation reaction. Fortunately for us, that means we can just multiply our oxidation half reaction by 5 to get up to 5 electrons. So we're going to do that in Orange Go Giants. So we have to multiply all of those things by 5. So we'll end up with 5 Fe2 plus goes to 5 Fe3 plus 5 E minus electrons. And now we can add them together and cancel things out. And I'll do that in blue. So we've got our 5 iron 2 plus 5 electrons plus 8 H plus MnO4 minus goes to 5 iron 3 plus 5 electrons, manganese 2 plus 4 H2O. And then we can cancel out our electrons. Electrons are the only thing that we've got the same on the left and the right, so that's the only thing we're going to be canceling out. And then just to check, just to be sure, we can verify that our mass is balanced. So looking at our iron, we've got 5 on the left, we've got 5 on the right. Our manganese, we've got 1 on the left, we've got 1 on the right. Our hydrogens, we've got 8 on the left, 4 times 2 is 8 on the right. We've got 4 oxygens on the left, we've got 4 times 1 oxygens on the right. Then for charge, we've got 10 plus 8 plus 1 minus, so 17 plus on the left side. We've got 15 plus 2 plus, so 17 plus on the right side. I don't expect you to necessarily be doing that all in your head. I just ran out of space, and so I'm doing it that way. Questions about this middle difficulty redox reaction? Yes? If we have oxygen in one or both half reactions, yes, we balance that with water. Then we balance the hydrogens with H+.
And that's all in one half reaction, right?
It could be in both half reactions. That's part of why I was saying this is a middle difficulty redox reaction.
Are we going to do that next?
It might be the next slide. I don't remember. Other question?
I was just going to ask if that's how it's written in final form, or can we write it without the electrons?
I crossed them out. I would rewrite them without, like, remove everything that we canceled out, just so we've got a nice, clean, and tidy end product. Yeah. Do we want to do another one in acidic solution? All right, we'll do another one in acidic solution. Okay, what's our first step? We assign oxidation numbers. We've got copper gets a 0. We've got then copper 2 plus, which gets a +2. We've got our nitrate ion, and we've got nitrogen dioxide. So in nitrate, oxygen gets its preferred -2. In nitrogen dioxide, that's also true, because oxygen comes before our 5A groups. It's fluorine, hydrogen, oxygen, 7A, 6A, 5A. And then our nitrogen will take up the balance. So we've got -6 total coming from our oxygens. We have to total up to a -1. So our nitrogen then has to have a +5. The same idea, but it's neutral for our NO2. So oxygen's bringing a total of -4 to the table. We need it to balance out. Nitrogen's going to take on the balance, so it's going to be a +4. And then, what do we do? Separate them out. So we're going to put our copper on one side. Is this our reduction or our oxidation half reaction? This is our oxidation half reaction, because copper is going from a 0 to a +2. Its oxidation number is going up, so it's being oxidized. Our other half reaction is nitrate going to nitrogen dioxide. This is our reduction half reaction, because nitrogen is going from +5 to +4, which is reducing, or a reduction in number or size or quantity, whatever you want to call it. Now what do? We balance mass. Nice, our oxidation half reaction is done for mass. For reduction half reaction, you've got nitrogen. We've got 1 and 1, nice and easy. We've got oxygen up next. We've got 3 on the left, 2 on the right. So we need to get that 2 up to a 3, and we can do that by adding in water, because water is floating around. It's in aqueous solution. It's also acidic. So now we've got our 3 oxygens, but now we also have hydrogens. So to balance out our 2 hydrogens, we can add in 2H+. So now we've got a charge of 2 on, hydrogens that are 2 on the left, 2 on the right. So we're balanced with respect to mass. What else do we have to balance for? Yeah, we have to balance for charge. So taking a look at our charge, we've got a neutral charge in our oxidation on the left, and we've got a 2+ on the right from our cupric ion. To balance that out, we can add electrons. Electrons are negatively charged, and so it will bring down the charge of whatever side it's on. So we're going to add to the higher charged one 2 electrons, and that brings us down to neutral. We also get to do this for our reduction half reaction. On the right side, we've got a charge of 0, no charged ions or particles over there. On the left side, we've got 2 H+ and 1 NO3-. So we've got a 1+. To get that to balance out, we add in an electron to bring that 1+ charge down to a 0. What's next? Yeah, we have to balance with respect to our electrons. We've got 2 electrons in our oxidation half reaction. We've got 1 electron in our reduction half reaction. So we can double our reduction half reaction. So we get to multiply all those coefficients, the numbers in front, by 2. And to make this fit, I'm going to shrink my balancing. And this is where a lot of mistakes can be made. It's the simplest part, arguably. One of the simpler parts, at least. But it can be hard sometimes to remember to distribute the 2 to everything. All right, we've got our 2 electrons. We've got our 2 electrons. Now it's time to combine. So I'll write the copper one first. Copper plus 2 electrons plus 4 protons plus 2 nitrates goes to copper 2 plus 2 electrons plus 2 nitrogen dioxide plus 2 H2O. And then we can cancel our electrons. And then if we really wanted to, we could go back through and check, verify that everything's correct. We'll do that real quick. Copper, copper, hydrogens, both 4, 2 nitrogens, 6 oxygens, 2 times 2 for 4, plus 2 times 1 for another 2 for 6 oxygens. And then our charge, we've got a total of 4 plus 2 minus for 2 plus, and 2 plus on the right side, so our charge is also balanced. So we're done. Again, this is not the most difficult that redox reactions can get. Because you could have balancing on both of the half reactions. That would make it more difficult for acidic solution. Any questions about balancing an acidic solution? What's the opposite of acidic? Basic. We can also balance in basic solution. Okay, so balancing in basic solution has one additional step. This is not the only way that you can do this. I think this is the easiest way that you can do this. So what we're going to do is we're going to do the exact same thing that we did with acidic solution. So point 3, balance each half reaction with respect to mass in the following order. Balance things that aren't hydrogen and oxygen. Balance oxygen by adding H2O. Balance hydrogen by adding H+. If we stop there, what's the problem? If there's H+ floating around, then it would be acidic. We are in basic solution, and so we have an excess of hydroxide, or OH- floating around, so we would not have any H+. Why this can become difficult is if we're adding hydroxide, we're adding oxygen and hydrogen. And so that could screw up our balancing. So the way that we do this is we neutralize any of our H+. If we add hydroxide and H+ combine, it forms H2O. You would also add the same number of hydroxide ions to the other side of the equation. So this is the only part that's different. So neutralize H+ by adding hydroxide to both sides. And H+ plus OH- equals H2O. So we'll turn that side into H2Os, and magically we'll have the correct number of hydroxides on the other side. This is how we complete the mass balancing portion. We still have to balance for charge, multiply to get our electrons equal, combine them, cancel things out. But this lets us just do one extra step instead of potentially a lot more math. So this is the way that I recommend doing it in basic solution. So here's what that looks like. We're balancing this redox reaction in basic solution. Everything is basically the same, except for that one step that we just looked at on the previous slide. So for our oxidation states, we've got -1. For our I-, we've got a 0. For our iodine, we looked at permanganate earlier, so I'm just going to give those the +7 and the -2 that they get. And then for our MnO2, our oxygen is going to have a -2. Our manganese is then going to have a +4. We separate them out into oxidation and reduction. It doesn't matter which one goes to which side, or if you stack them, if you've got space. So I- going to I2. We went from -1 to 0, so this would be our oxidation reaction, half reaction. We've got permanganate MnO4- going to manganese 4 oxide, MnO2. This is our other one, so it's our reduction half reaction. It also went from a +7 to a +4, which is a reduction in oxidation state. Now we balance with respect to mass. For our oxidation half reaction, we've got 2 iodines on the right, 1 on the left, at a coefficient of 2. We're done balancing our oxidation half reaction. For our reduction half reaction, we're balancing things that are not oxygen or hydrogen. Our manganese is balanced. The other thing that we've got is oxygen. We've got 4 on the left, 2 on the right. To get those balanced out, we can add water. We're still in an aqueous solution, so we can add 2 H2Os. Now we've got our 4 oxygens on the right side. We also, when we did that, added in hydrogens, so we need to balance our hydrogens. We've got 4 hydrogens on the left. We've got 4 on the right, 0 on the left. So we need to add, pretending, just for a moment, like we're in acidic solution, we're adding 4 H+. So that gets our hydrogen balanced. And now this is the important step. If you forget that we are in basic solution and you just continue going on this way, you will get the wrong answer because you'll have balanced it for acidic solution. And at the end, I'll mark you, hey, you balanced it for the wrong thing, take a couple points off. We can't have H+ floating around in excess in solution when it's basic. Since we're in basic solution, we're going to add hydroxide to balance out our H+, our hydroniums. So we've got 4 hydrogens on the left side. How many hydroxides do we need to balance out our hydrogens? 4, same number. So we're going to add 4 hydroxides to both sides. The nice thing about this is we did an equal treatment. We did the same thing to the left as we did to the right. We have not changed our mass balancing. Our mass is still balanced. So we don't have to recheck it as long as we're sure that we added 4 to the left and 4 to the right. Pretty easy to not screw that up. And now we're balanced with respect to mass. We still have to balance with respect to charge. So to balance with respect to charge, just business as usual, counting up our charges, adding electrons. For our oxidation half reaction, we've got 2 I-. So we've got a 2 negative charge on the left, 0 charge on the right. What side are we adding our electrons to? When we're adding electrons, they're negatively charged. They can only reduce our charge number, so we have to add the electrons to the right side, the side that's on the right, which is also the correct side. For our charge, if we want to, we can turn these H+ and OH- into H2Os. That helps simplify our charge calculation a little bit. We've got a 1- charge on the left. We've got 4 hydroxides on the right side. So we've got a 4- charge on the right. That means that we have to add electrons to the left side. We need to add 3 electrons to the left side to get our -1 down to a 4-. Any questions so far? Great. Now what do we need to do? We need to check and make sure, do we have the same number of electrons in each of these? So in our oxidation half reaction, we've got 2. In our reduction half reaction, we've got 3. Unfortunately, those are not the same number. And we can't multiply one by a number to get to the other, so we get to multiply both of them by something. So again, our least common multiple for 2 and 3 is 6. So we get to multiply by 3 for our oxidation, by 2 for our reduction. Oh, don't do that. So this turns into 6I minus. 6I minus goes to 3I2 plus 6 electrons. We've also got 6 electrons plus 8 H2O plus 2 permanganate goes to 2 MnO2, 4 H2O, and 8 hydroxides. Now we can combine them. So combining these together, 6I minus, I'm just going to not narrate the whole thing. We get this whole thing. What fun. And then we can cancel out our electrons. And we're done, right?
Gotcha.
Right? Aren't we done? We're not done. And not just because we didn't check it. We've got 8 waters on the left. We've got 4 waters on the right. We can cancel some waters out. So remove 4 H2Os from both sides. Becomes 4 H2Os on the left side. We could have also just canceled the H2Os in our reduction half reaction before we combined them. And now we can check. So moving through, we've got 6 iodines on both sides. 3 times 2 is 6. We've got, let's do manganese next, 2 and 2. We've got hydrogens. We've got 4 times 2 is 8. We've got 8 on the right side. For our oxygens, we've got 4 times 1 for 4, plus another 8 for 12. We've got 2 times 2 is 4, plus 8 is 12. Mass is balanced. That's great. For our charge, we've got 6 minus and 2 minus for a total of 8 minus on the left side. And we've got 8 minus on the right side from our hydroxides. So we are all balanced out. This is a slightly higher than middle difficulty redox reaction problem. And then if you really wanted to, you could do this one. If you'd like to do it and check it with me, you're welcome to do that. This is probably about the max level difficulty for this class, and that'll do it for redox reaction balancing.